Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Blower Technologies and Energy Efficiency Opportunities. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders past, present, and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Kaiser Compressors. Kaiser Compressors is one of the world's largest compressed air systems providers and compressor manufacturers. From its state-of-the-art production facility in Germany, Kaiser works in close partnership with its customers to develop progressive system concepts that continuously push the boundaries of performance and compressed air efficiency. The Kaiser product meets and exceeds Australian conditions and regulations, and the standard machines are suitable for continuous operation at ambient conditions up to 45 degrees Celsius and higher. Today, we will hear from two speakers followed by a live audience Q&A. And I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to welcome our first speaker, Jeff Cohen. Jeff is the National Design and Engineering Manager at Kaiser Compressors and has over 14 years of experience in the compressed air and blower industry. Jeff leads the National Design and Engineering Department at Kaiser, where they technically support the broader community within Australia and New Zealand, as well as specialising in designing, engineering and manufacturing custom products for large infrastructure projects and mining applications. Please welcome Jeff Coyle.
Hi everyone, my name's Jeff Coyle and I'm from Kaiser Compressors in Melbourne, Australia. And today I'm going to be talking about low pressure blower technologies and energy efficiency opportunities. So I'm just going to be going over this subject fairly briefly, and then there'll be more details in the next presentation. So we'll launch into it. And so firstly, what I'm going to be going through, I'll be going through some of the applications for low pressure blowers, air compressors essentially, and then I'll be going through some of the blower operating principles and then touching on specific power and explaining that a little bit and why it's important. Then going into packaged blower units and energy efficiency in correct control, because that's important for a modern low pressure blower station, and then summarising. So firstly, let's look at some of the applications that we might use some of these air blowers for, and you can see there we've got a couple of air blowers there. And the main one that we see in Australia, and it might be around the world the same, is for wastewater treatment plants in introducing oxygen into the water basins. And that's what that picture there on the top sort of represents. So what it's doing there is it's blowing low pressure, high volumes of air into the water column there. And again, this is outside the area of my expertise because I'm a compressor person, but they're essentially blowing bubbles into that water to introduce oxygen in there so that the little microbes in the water can do their job in decomposing and breaking down that sewage that is in there. So and there you see some of those basins in aerial view on the bottom right there. So that's what the main application for blowers is in Australia. Now, it'd be the highest percentage of blowers in the market there would be for either water treatment plants or wastewater treatment plants or sewage treatment plant. And there are other applications as well, which I can sort of show you now. And here's the top two photos there. The little aerators that are in the bottom of the basin. So obviously those two photos don't show that there's water in there at the moment, but there's different types of, aerators and that sort of thing that the air can get introduced to the water to. And another application, which is also is within the water treatment plant, would be backwashing filters. So often in some water treatment plants, there are very large filters in there with some sort of filter bed, and they blow low pressure air over them to get rid of all the contaminants out of the bed. And that's what that bottom picture there is showing, a cross section of such a filter with a air for backwashing. So that would be a separate blower system for that. So again, they're sort of, as a percentage, probably the most used application for low pressure air blowers. Another popular use for low pressure air blowers would be pneumatic conveying systems. So this is where we have a little a blower blowing air, and you can see that on the bottom left of that little schematic there. And then we introduce a medium into that air stream via a hopper, and you can see that hopper there. It could be anything from, like, a feed truck has one of these systems on it to blow the feed out into a silo, or cement plants, or anytime you need to move fine product, you would do that with pneumatic conveying. So the product is sprinkled into the airstream, and then it's blown into another hopper that is vented there. So you can see that little schematic there. That's called pneumatic conveying. In that instance, we would use a low pressure blower. When I talk about low pressure, I'm talking about an air pump of some description that would go up to a maximum of about 1 bar gauge. So that's twice atmospheric. And we class that in the industry as a blower. And I'll go into the different technologies that can produce that. But that's what these sort of the range of pressure, I'll say, that we're talking about is up to 1 bar gauge. So a typical water treatment plant would use around about half a bar gauge pressure to aerate that water. Pneumatic conveying systems probably would be a little bit higher than that, maybe up to 0.8 of a bar to sort of transport that medium there. So there are two examples. Now there's obviously a lot more uses for low pressure air like this, whether it be some sort of drying system in a manufacturing plant, or air knives, or even running these in reverse, so centralized vacuum systems. You can get these that run the other way to create a vacuum. Very useful types of equipment for low pressure and high volume. That's I guess the key. They can pass a lot of air, or pump a lot of air at low pressure. So obviously these are the different types of compressors, or compressor technologies and principles, I'll say, that is out there in the world. Obviously I'm coming from a manufacturer's point of view. The company I work for, KZ, we don't sell all these, but this is what is available out there in the world. And some of these are high pressure and some are low pressure. So I'll just quickly go through it and point out what technologies do fit within this low pressure sector that we're talking about today. And that is up to 1 bar gauge. So on the left, we have dynamic compressors, and that's where we're using kinetic energy and converting that into pressure energy. So the most common would be like a radial turbo compressor. So much like the turbocharger on your car, that is essentially an air pump, and that's quite popular to use in very large applications for low pressure equipment, multi-stages or single turbo, which I'll discuss a little bit later on. But you've also got radial and axial. They're like a jet engine, essentially. They would be very, very large, either mining or something like that, where they might need, low pressure for like flotation mining. Often that does actually require a little bit over 1 bar, but that's a typical application for a very large compressor like that. Obviously moving on to displacement compressors on the left there, and that's very typically for higher pressures, but there are some low pressure blower technologies within that, and it's really in the rotary compressors there. you can see we've got one shaft and two shaft there. So when we're talking about low pressure, probably the most common sold low pressure blower would be a rotary Lobe blower, and you can see that it's a double shaft one, and it's the second one from the bottom. That's very typical. And in the old school terminology, we would call it a Roots blower, but Roots is actually a company that make them. So yeah, it's technically a Lobe blower. And we also have a screw compressor there, so you can get screw blowers, which I'll talk about later on as well, for low pressure sector. So they're the two key ones, I would say. And then on the very right-hand side of this little map, we've got piston compressors. And, I don't think you would use any piston compressors for low pressure applications, just because of, I guess, the maintenance needed for a piston compressor. And piston compressors really come into their own at very high pressures. That's where they're really used for, where you multi-stage them to get extreme pressures for pet bottling or diving, those sorts of things. So, yeah, I think that the three main ones would be, a dynamic compressor would be a turbo for the low pressure sector, as well as, the rotary Lobe blowers and rotary screw blowers. And of course, there are other technologies, but I'm sort of really, the focus for today is industrial sector, high duty, energy efficient. And they're the three for an industrial sector for low pressure blowers. Yeah, so as I said, these are two examples, and I'll cover the third later on. But as I said, the most prolific would be actually this bottom. I guess you could call it a cutaway look at a rotary blower, and it shows the stages of the air moving through the block. We call it. That's the pump, the blower block. So the air is introduced in the top, and it moves around the outside of the lobes and gets essentially sort of pushed and squeezed out the bottom. So the difference with a rotary Lobe blower like that, and if you wanted to see one of these moving, you just type it into Google, rotary blower, and you could probably see a little animation of how this works better than I can explain it. But yeah, they need a back pressure, essentially like a head of water or some sort of restriction in the pipe to create the pressure. That's what we call, external compression. There's no compression happening inside the blower block itself. That needs to happen externally, and you do need to have, a restriction there or a head of water or something for the pump to work against to create the pressure. Whereas the top images, we see that is a screw compressor element, and that's, again, the pump. They're like a Lobe blower, but they have a twist to them. And that does create internal compression, as it says there. So because those rotors are coming together and they're changing the volume inside the screw, or changing the trap volume, that's obviously displacing the air and compressing it, and that's internal compression. So these are very good for higher pressures. And obviously in the industrial sector, a rotary screw compressor would be the norm, and that's up to 7 bar. But for the purpose of what we're doing here, you can get these in the low pressure sector. They're not as aggressive with the twist there, but they do have a slight twist and a slight internal compression there to get a bit more energy efficiency out. But obviously that comes as a trade-off in that they can be a little bit more costly to manufacture and produce. But very efficient blowers there. And they have internal compression. So both are displacement compressors, essentially. So here's a little chart, I guess, that shows a PD Lobe blower versus a screw blower and where you might use them. And again, this is very, very general, but I guess for the purposes of educating fellow engineers, you could say that a screw blower, you would want that because they do have internal compression to work at sort of pressures maybe over 400, 500 millibar to get value for money. And then a PD blower, they can work right up to 1 bar, no problem, but certainly come into their own at lower pressures. So if you have an application for, say, 300 millibar, that would be sort of nice to have that. So as a Lobe blower, essentially, you don't need that internal compression. So yeah, the other technology that we see in the industrial sector for low pressure air blowers would be the turbo compressor. So yeah, you can get, I guess, single turbine compressors and multi-stage turbos like the one on the top right there, where we have one stage compressing, and then it would get cooled and then go into the second stage and get compressing more to higher pressures. And often they have permanent magnet motors and lots of trickery in there because they do have limitations on control, as well as obviously you need to run these at very high speeds, sometimes up to 20,000 RPM, because we need to, I guess, flick that mass of air out the impellers. You can sort of see on that left-hand top image there, we've got an impeller and there's no housing there, I've pictured, but the air comes in and it gets flung out those vanes under centrifugal force and it's caught in the housing. And the housings are those blue and red ones in the other image. And it gets sort of shot out the top there. So that's essentially how the turbo compressor works. It's no different to the turbocharger you have on your car, but obviously a fraction larger. And yeah, that's a turbo compressor. So as I said, they can be, quite efficient at a set point, and that would be the key. And I'll touch on that a bit later on. And also, they are affected by ambient conditions quite a lot because obviously the mass of the air is crucial to creating the pressure. And with different temperatures, the mass of the air changes. So you obviously with lighter air, so less humid air, the pump needs to work more to create the pressure because it's less mass. So yeah, there's things to consider. So certainly, if you're looking at turbo compressors, you will need to speak to experts about how to go about designing that. And I think the next presentation will touch on some of those key principles. But there is a lot more to think about with a turbo compressor in regards to design and how we go about design and keeping it quite smart in design. And here's, I guess, three main blower principles that I've sort of covered in the graph showing on the bottom air delivery changing, and on the left axis we've got specific power or power consumption increasing. So you can see turbos are good at a set design point, at the bottom of the curve essentially there. They're happy running there, and once you start going higher or lower in the flow ranges, they do suffer a little bit, and that's because they have limitations on control range when you're hitting surge points and all those sorts of things. So as far as PD blowers, you can see they do use a little bit more power, but they are very simple and very cost effective to acquire and purchase. So there's always a trade-off, I guess, with anything in life. They each have their place, really. And certainly PD blowers are the most prolific out there that we see, for good reason. They're simple, they're affordable, and they're very easy to maintain and service. So, whereas turbos are very specialised and can be quite costly to overhaul. So a bit of food for thought there as far as efficiency. And you can see that we've got specific power as our power measurement, which I'll talk about later on. Actually, right now. Moving on to part 3 and specific power. So why am I talking about specific power? Well, obviously we want to make sure that we're anything we're designing, we're keeping it the most energy efficient we can. And this is specific power is a unit of measure that us in the industry use to benchmark equipment, electrical equipment, so that we can see that we're talking apples for apples, or we can make smart decisions on asset purchases based on power and those sorts of key critical factors. So specific power is at the bottom there. It's explained as the total power input to the unit divided by the air output or the air delivery. So it's a unit essentially, and you want it to be as low as possible. So you want to have the least amount of power to produce essentially, say, 1 cubic meter, a measure of air. So obviously, the ISO there, which is the international standard body, has come up with ISO 1217, which is actually an air standard for compressed air. So, a good reputable manufacturer like Kaiser, us, we guarantee our machine's performance to ISO 1217, and that is the package power. We're not talking about blower shaft power, nothing like that. It is the total input power to the blower box, like that picture we've got there on the bottom right. That's a blower. The total power going into it, divided by the free delivery, we get a unit, specific power, and then we can do energy calculations with that and see how we perform to different technologies, say, a low blower versus a turbo, or different manufacturers versus different manufacturers, or existing versus new. So things like that, we can use these figures to do nice energy calculations to make sure that, if we're designing something and putting something in new, that, we do that properly and thoughtfully about energy saving. So that's specific power. And certainly there's more information on the internet about that if you want to do some more reading. So what affects power consumption? Obviously, there's lots of contributors to power loss. And we have obviously drive systems where they're pictured in the middle as a belt drive system. Obviously, there's losses in that. Maybe you want to look at direct drive blowers, which are available. Obviously, electric motors, you get different efficient electric motors. Internal components like that's the inlet silencer there, the flow through that obviously can restrict the inlet pressure, creating more power usage. Frequency drive systems also have losses in them. And the block itself, like how refined is the blower pump, and is it efficient? They all contribute to power loss. And why are we talking about this essentially? Why am I here talking about low pressure blowers? Well, most towns and cities have water treatment plants because our sewage needs to go somewhere. The industry is saying that 50% of those sewage treatment plants' power usage is related to a low pressure blower. So they have huge motors in them sometimes. Not uncommon to have over 100 kilowatt motors in these blowers, and maybe 4 of them on site. They're huge power consumers. So that's why I'm here, and that's why we're talking about this, to create awareness that this is, in my opinion, the first point of call with a treatment plant, or even anything like a manufacturing plant that had pneumatic conveying or whatever. They do consume a lot of power. So we need to start the discussion and really highlight this to people, that if you want to save energy, maybe look to these sorts of pumps as to a first point of call, maybe. So packaged units, this is a bit more about the blowers themselves. Obviously you can get them, they're all mainly, a lot of them are custom made to order because we have different pressures and flows and all those sorts of things. So there's lots of things to consider. We have a lot of control in them these days, and there's listed some of the senders and monitoring that you can have. So they also have PC-based controllers attached to them, and frequency drive systems. So obviously monitoring and control is a big part of a modern blower station and keeping it efficient, because you can have the most efficient blower in the world, but if you're not controlling it in a smart and intelligent manner, it's a waste of money, because it could be running unnecessarily or switching a lot, creating losses there. So that's why PC control, whether it be onboard PC controllers there, or on the bottom there we've got a master controller which could control big banks of blowers in a smart and efficient manner. So looking to control is as important, in my opinion, these days in a modern any air compressor station, whether it be high or low pressure, is very important. So again, if you need any more information, then speak to manufacturers about it or experts in the field, because it's a very important sector. So that's obviously a lot of information from me in a quick time frame, but I guess it was a general introduction to low pressure blowers. And as I said, they are large energy consumers. That's why we're here talking about it. And there's a lot of different options out there in the moment: turnkey blowers, with or without frequency drives, all those sorts of things. And as engineers, you should always look to the ISO standards for benchmarking. That's important that everyone talks apples for apples. And also referencing specific power is key, so that we can also look at the right figures when we're designing, and control is very important these days. So that's it from me, and thanks for your attention. And it's been great to speak about low pressure blowers here today.
Thank you, Jeff, for your insights. I'd now like to welcome our second speaker, Hiran Demel. Heron is a senior project manager and engineering technologies expert with more than 35 years of global project delivery experience. He has significant experience in water and wastewater treatment, condition assessment, process facility design, construction startup, troubleshooting, testing, and optimizing large mechanical and electrical systems with complex controls. Hiran has worked as project manager, design manager, senior consultant, quality control reviewer, and technology specialist, and is a leader in compressible and incompressible flow modeling, system design implementation, and the advancement of CH2M, now Jacobs. Please welcome Hiran Demel.
Hello, Amanda. Thank you. Hello, everyone. Thank you for that introduction. I would like to talk to you today about blower technologies and some of the blower technologies specifically used in the water wastewater industry. My background is in water wastewater, so that's the area that I will focus on. So some of the topics I'm going to cover today are basically blower technologies typically found in water wastewater industry. There's positive displacement blowers, single-stage centrifugal blowers, and multi-stage centrifugal blowers, and high-speed turbos. Those are kind of the main four categories. Now, there's other blowers that we use, but I'm not going to focus on that. Those mainly focus on these blowers, all right? Typical blower applications, then I'll also talk about the typical blower applications associated with these types of blowers, and then also give you some guidance on how to evaluate these systems and some things you need to consider. Okay, so when it comes to blowers, I believe there's mainly two different kinds of blowers. There's the positive displacement blowers, which is just like a PD pump. It's a positive displacement machine. And then there are centrifugal blowers. So as you see, there's what it says, positive displacement, and then all of the others are actually, the other three categories up top there, they're all centrifugal family of blowers, okay? Similar to a centrifugal pump. It has an impeller, rotating impeller that uses the centrifugal forces to generate the pressure, whereas with the positive displacement blower, you have a rotor stator kind of arrangement that pushes the flow through the unit. All right. So starting from the bottom left, you got Lobe type blowers, and that is that they got typically in a Lobe type blower you would have tri-lobe or dual lobe impellers. Okay. And then there's also another type called screw type blower, right? And that's you see a picture of a screw impeller. Then when it comes to the single stage centrifugal blowers, you got single point control or dual point control. Single point control means that you got just inlet guide vanes that control the air flow and pressure. And then dual point control is you got both inlet and discharge vanes that control the flow, pressure, and the shape of the curve. And then you can also have single stage machines just connected to a variable frequency drive, typically in these single stage machines, they are also high speed blowers. So they also have this sort of impeller that you see in the middle there below the blowers. Then when it comes to multi-stage blowers, you can see the cutaway, you see the different types of impellers. There's multiple impellers in blower, and those the multiple stages give you more pressure increase. Every stage adds pressure. And you can also, with multi-stage blowers, you can use different types of impellers to change the shape of the curves. Then you have the high-speed turbo gearless turbo. You have high-speed gearless turbo blowers. These blowers come with direct drive or direct drive. They're direct drive. There's no gearbox. And typically you have two different types of blowers. There's air bearing or mag bearing. So, and they have a VFD that controls the amount of flow and pressure that's generated. So it all are typically on a high-speed turbo blower. The VFD and all of the controls and the blower, everything is in a box, and the impeller is very essentially similar to the single-stage machines, and plus it's a high-speed machine, as I mentioned. Okay, going to the next slide. When it comes to rotary positive displacement blowers, now these blowers have been around since the 19th century, and they are, I believe, the mid 19th century, and they were initially invented by, they were also known as roots blowers, and roots blowers, I mean, typically now many different, a lot of vendors have adopted that design. They've rotary lobe blowers are ideal application of rotary lobe blowers are very small to medium size plant, variable depth reactors, where if the water level varies, be it in a digester or something like that, that's a good application for a positive displacement blower. Or equalization basins where you would have the water level fluctuate off, or a filter air cover system where you want to use these blowers to as filters cover air, or in a sequence batch reactor where you have a lot of starts and stops. The real advantage is that the rotary lobe blowers they don't cost. The initial cost is pretty low, simple control systems, high operating efficiencies at low pressures, and capable of operating against varying pressures. Ideal for, actually they're good for, like, if you have an engine-driven system, they work very well. They're also good for pneumatic conveyance. Now, one of the other things that I forgot to mention is that with the positive displacement blower, the air is just moved through the blower. You can see those the diagrams just below the blowers. You show the air moving essentially from left to right there on a rotary lobe blower, and then you see with the tri-lobe, you see on the right-hand side, they are moving in these from from top to bottom. But here's what's important to remember: you don't generate pressure in a rotary lobe blower. You just move air through the blower. The pressure is generated outside. There's no compression that happens. So the volume, whatever volume that comes in the blower, is moved out. But whereas the pressure is generated outside the blower. So the real disadvantages with this blower is that the efficiencies are generally lower than if you were looking at centrifugal blowers. They do generate quite a bit of noise. They also have noise, and there's a pulsation, because depending on the number of lobes you have, you could have a pulsation. So you do need to have silencers and sound, and typically you do have silencers and sound enclosures around. The only way to really control the flow is to utilize VFD, because you cannot control it by closing a valve. In fact, you shouldn't ever close a valve on a positive displacement blower. Generally, they do require more maintenance than centrifugal blowers, but for a small, medium-sized plant, that typically isn't a big issue. Normal power range is from about 4 to 200 kW. So they essentially do run in small sizes. So if you're looking at a large plant, you probably wouldn't be using these blowers. One good thing about these are that they're typically they do come they can come with a VFD or a belt-driven unit, and you can achieve more than a 50% turn down. So that's a good thing. So you can cover a wide range of flows. Okay, the next blower type I would like to talk about is the screw positive displacement blowers. Okay, this actually has, as I showed on the initial slide, they have a screw that actually does provide some level of internal compression, which means it does help with some energy savings over a Lobe type blower. For instance, this diagram that you're looking at, the PV diagram you're looking at, the blue kind of shows the energy typically on a Lobe type blower. The green is not there because you don't get any compression, right? So the energy savings due to internal compression is not there on a Lobe type blower, where with the screw type blower, you do get that energy saving. You can run these as constant speed blowers or as variable speed blowers. And so in the case of if you have a variable speed drive, then you can adjust the flow. Otherwise, it's the same flow, and there's really no flow way to control the flow. All right. So again, these are good for small to medium-sized plant. This is a little bit of a newer technology than the rotary lobe. Good in the same applications. Simple control scheme, high efficiency versus the Lobe type blower, as I mentioned. They're a little bit less noisy than the Lobe type blower, capable operating against varying pressures, typically better turn down than centrifugal blowers. Okay. Disadvantages. Higher first cost than the Lobe type blowers, must vary speed to vary flow. Most maintenance, little bit more maintenance than a centrifugal blower. Typically located in a blower building because you do have a lot of electronics. In fact, you can see the picture on the left shows a constant speed blower, and you can see the electronics cabinet is open. Picture on the right-hand side shows the variable frequency blower. And you can see there's a VFD in there. So, all right. Okay, so next is probably the most popular blower in the industry, and it really is the workhorse of the industry. These blowers the multi-stage centrifugal blowers can be installed outdoors. You can have a combination of impellers as well, depending on what kind of pressure and what kind of turn down you're trying to generate. You can match different impellers and achieve a different shape of the blower curve. Lower pressure ranges, you can achieve lower pressure ranges than with PDs, better efficiency than PDs typically. They are direct drive units. They go only up to about 3,600 RPM. However, you do need to pay attention to turn down capability, because a lot of the times, if you do need to achieve what they call enough turn down so you don't have gaps in operation, then you got to really select the blowers in a fashion that there is enough overlap. So you really need to look at the blower curves. Now, this is true about any blower, actually. You need to look at the curves. You need to look at the blower curves, not just at your maximum or minimum conditions under, let's say, summer conditions. You really need to be looking at under all conditions, be it winter, summer, spring, and look at your minimum, maximum flows. Make sure that the blowers can achieve your minimum, maximum flows under any seasonal conditions, and that you don't have any gaps in operation. So, anyways, the main advantage with multi-stage blowers is they're, again, low cost, low noise and vibration levels. It's established technology, been around for a long time. Similar operation and maintenance, simple operation and maintenance, and they're quite reliable. Plus, as I mentioned, they are running at 3,600 RPM typically. And so they're not a fast-moving piece of machine. And they really are the workhorse. One thing really beneficial about multi-stage centrifugal blowers is, I call it, it's good for, but if you have a lot of high flow demand, and if you are especially in a bigger plant, you can use these to do what I call base loading, right? You can use them along with some of the other blower technologies, which provide you better variable flow control. And you can use these as your base load, and then you can use those variable speed blowers or variable flow blowers to control the variable flow demands in your system. So this way you can run the multi-stage blower at its most efficient point, and then use those other blowers to meet your variable flow demand. Okay. Typical disadvantages with these is they're less efficient, right? Limited turn down, 50 to 70% capacity. Efficiency at 100% capacity is a little bit lower than a single stage machine, which we'll talk about here in a minute. Rapid loss in efficiency, especially if you can also use what they call inlet throttling. And if you do inlet throttling, then you will lose efficiency quite rapidly. But if you're using a VFD, you can most of the time maintain pretty good efficiency, but you won't, unless you have a very steep curve, it's hard to throttle these blowers. It's hard to reduce flow on these blowers. So it's best to use them at their peak flow, peak efficiency range, and then use, let's say, another blower, be it a single stage or a high-speed turbo blower, as the variable flow blower. Okay. One thing also to keep in mind is they are susceptible to surge, as if the discharge pressure is too high. So you got to make sure that they don't run into surge. And that's actually true with any type of centrifugal blower. Okay. The diagram on the right left, on the right top shows what's in a blower package typically, right? You got a inlet filter, silencer, inlet valve. Then you have the compressor, you have the motor, and then the local control panel, and then you also have a blow-off valve. That's especially during startup, you would have the blow-off, and then you have a discharge. You have a check valve, and then also have a discharge. That's a typical installation of any centrifugal blower. Okay. Next, we're going to talk about integrally geared single-stage blowers. Integrally geared single-stage centrifugal blowers also have been around for a long time, quite popular. Globally, they've been used in water, wastewater applications, plus also in a lot of industrial applications, actually. Commonly used in large plants. Now you're actually starting to get, they are making smaller single-stage blowers, but when they first came out, they were only available in the larger sizes. They're good they're good in a constant depth react. They're typically good to be used in a constant depth reactors, but you can use it in if the flow varies, but not rapidly. That's when you would want to use what we talked about, a PD, some type of a PD blower if the flow varies rapidly. It's essentially good in a varying flow application similar to the multi-stage. Good application would be a medium to high pressure flow applications. This is the ideal blower for that type of application. Okay. Advantages. They're probably the most efficient, one of the most efficient blowers in the market. And they also provide good turn down capability, typically from 100 to 45% capacity turn down. Maintains a high efficiency throughout, and it's a well-established technology. Okay. Intricately geared single-stage machines are what I call a high-speed machine because they rotate. The blower rotates at about 20. Typically, they can go up to about 20,000 RPM. So, one thing keep in mind is that the initial costs on these blowers can be a little bit high, and they relatively do have high maintenance, especially comparing with if you compare it to a multi-stage blower, it does cost quite a bit to maintain. Most installations have a service contract with manufacturers for preventive maintenance, especially if they are not familiar with the technology. They'll have some kind of a maintenance agreement with manufacturer. Okay, next slide. Okay, I'm going to show you some cutaways of the intricately geared single-stage centrifugal blower. Okay, what you're seeing here is just a cutaway of the blower, and you see the inlet guide vanes, and then you'll also see the discharge vane on the. I know it's probably hard to see it in the picture, but you see the impeller. Just around the impeller, you'll see the discharge guide vanes that control. So there's an inlet guide vane that can throttle the amount of air that comes into the blower, and actually it shapes the air that comes into the blower towards the impeller or away from the impeller, and you can control the flow that way. And then the diffuser discharge vanes actually adjust the shape of the curve of the blower curve, and you see a blow up of the diffuser discharge vane. All right. So in the blower package here on the right bottom, you see the different components that are there. I'll just flip through it real quick. Okay, and the next category is the high-speed gearless turbo blowers. Okay, these are ideal for constant depth reactors, again, varying flow applications, and low to medium pressure application. But typically, you will see high-speed turbo blowers in a small to medium-sized plant. In large plants, you would essentially have to have it just wouldn't be practical to have a lot of high-speed turbo blowers. Okay. Okay, the biggest advantage about the high-speed turbo blower is that they do provide the efficiency, but they cost less than a single-stage blower. Okay, and it is a small footprint, therefore reduce building costs. The integrated package is, while most vendors say they're just plug and play, I say they're not necessarily plug and play because you really need to think about where you install these and how they're located in what kind of environments, and we can talk about that here in a minute, and I'll show you some installation pictures. Very few moving parts. That's one of the biggest advantages. Most of the blower there's a lot of electrical and electronic components you'll see here in a minute, But as far as moving parts, there's very few mechanical moving parts. So that's probably the biggest advantage. So from a maintenance perspective, from a mechanical maintenance perspective, it's pretty low maintenance. Okay. And the other main important thing is they don't require any kind of oil lubrication. It's typically high-speed turbo blowers come in two types of high-speed turbo blowers. You get the mag bearing or the air bearing. Both do not require any kind of oil lubrication or grease lubrication. Routine maintenance is typically you just need to change the air filters. They are quiet, so typically they operate around under 85 dB or so, and they essentially come with a sound enclosure around them. So it is relatively new technology. You can get the package is all integrated. It all comes in a box, basically. High-speed turbo blowers do have what they call a permanent magnetic motor and a VFD and use a VFD to control the flow. They also have harmonic filters to eliminate the low harmonics or high harmonics. There's no contact bearings. As I said, there's air or magnetic field. They rotate within an air or magnetic field. However, they do rotate at a very high speed, about 30,000 RPM. You can achieve pretty good turn down, about 45 to 50% turn down. Proper inlet filtration is very critical with these blowers. You can't just install them in a dirty environment and expect them to work. As I mentioned, there's a lot of electronic components, and they are susceptible to corrosion. I don't necessarily advise people to install these blowers outdoors because, as you will see here shortly, there's a lot of electronic components that needs to be protected, just like you would in an electrical room type installation. If you were a typical electrical room, retrofitting in an existing facility can be a challenge, but we do it. But you have to pay close attention to what the environment is like and where it's going to be installed. Okay. So what's in this high-speed turbo? I mentioned that there's a lot of different components. Okay, so you do have a motor and a blower, just like you do with any other blower. However, you have a motor cooling fan, typically, and you have bearing cooling fan, pumps, coolant, all right? And then you also have all kinds of electronic filters like sine wave filters, variable frequency drive, harmonic filters, input chokes. All of these are electronic computers, all in this one box. Okay. And also local control panel, PLC, or process HMI controls, and miscellaneous electronic and power transformers. Okay. So I actually refer to this as an electronic air moving device. It's not what you consider a typical blower. The blower is just the motor and the blower and the motor, but look at all of the other components that are in this package. So this is why I say you have to really pay attention to where you install these blowers and what kind of inlet air you have coming into the blowers. Okay, this is a typical high-speed turbo blower. I mentioned there's two different configurations. This is a typical air-bearing machine. You see the cutaway, which is, or you see the one picture there on the bottom right hand. You see the blower components, and then also the electrical components. You see that's you're looking at a VFD, and then again with the package you got a lot of different components that make up the blower. Okay, And this is another view. This is where actually in this particular blower setup, you have two blowers in one compartment. And there you have another picture of the electrical compartment with the two VFDs in there. All right. This actually shows a picture of you can see the small air bearings or the larger air bearing machine. They're typically with a small air bearing machine, they're air cooled. With a larger one, you may have a pump at the bottom. That's the one that's shown on the right-hand side. You may have a pump. But you also have, okay, the animation that you see there kind of shows how the air flows through the blower through the motor, and then it takes the air, the hot air actually pulls it all through. So it really does keep the motor and the blower cool. The air actually helps to keep the motor and the blower cool. Now, depending on the vendor, some vendors have this the hot air that can be piped out. Others have it so that it all ingests the hot air from the process, from the compression process into the blower. So, in other words, the motor heat and the VFD heat and all that is ingested. Some vendors have it piped outside of the process air. Okay, here's another picture of the blower itself and the motor. You see the blower on the left-hand side, and it's a direct mounted motor. Okay. That's actually the impeller shaft. And here's the air bearing, right? That's this, when it rotates, this system just rides on this air bearing. You can see the airfoil bearing on the outside. Okay. This particular blower is a high-speed turbo blower that is a magnetic bearing. And the magnetic bearing is here on the bottom right hand. It is there's an impeller, okay, and then you have the labyrinth seals that go around it, and then you have the magnetic bearing, and you also have the permanent magnetic motor, and then you also have another magnetic bearing on the bottom. So again, this particular blower rides on the magnetic field, actually keeps the blower shaft suspended, whereas the previous one, it's an air bearing that actually keeps the shaft suspended and rotating. All right. And then, of course, there's a cooling fan as well. All right. These are some pictures of typical installations of air bearings on the left-hand side and mag bearings on the right-hand side. And as I said, I prefer to install these in a conditioned space. The bottom left-hand picture, you'll see there's a AC unit mounted onto the control cabinet of the blower. And I normally, especially if the building is not air conditioned, or conditioned in some way, then I would recommend installing those air conditions and units on the side of the blower control cabinet. That helps to keep the controls, think of it more like an electrical room, right? Typically we have electrical rooms that are, electrical rooms are typically conditioned in most wastewater plants. On the right-hand side, you see a mag bearing typical installation. One of the things I want to show you in the back wall there, you see that those are all harmonic filters supporting these blowers. All right. Okay. Lastly, I would like to leave you with a couple of references. The first is a book written by a good friend of mine called Tom Jenkins. He's also one of my folks I work with on blower stuff. And this is a very good book. It's called Aeration Control and System Design. It's a very practical book. So I would highly recommend, if people are interested more in blowers and how to size blowers, how to control blowers, or just the practical application beyond what you would learn in school, I would recommend getting this book. And then secondly, is a document called the ASME PTC 13 Wire to Air Performance Test Code for Blowers. This is a document that I have been worked with with a group of engineers and blower vendors in developing. It's a truly looks at the wire to air performance test of a blower, and I think it's probably the only document that really kind of captures all of this and how to really test blowers. And it also includes a lot of theory about how to look at different blowers, and really it eliminates the different. It helps you evaluate different blower technologies with one test code. Thank you.
To Hiran and Jeff for two great presentations. And I just want to draw your attention that Hiran is actually based in Florida in the US, and it's just ticked over midnight. So a big thank you for staying up to do this for us. It's now your turn to get involved. So you can please, if you could put your questions into the YouTube chat box and say who the question is directed to. And thank you also to everyone who put questions through whilst registering. And we might start with one of those to Hiran that's coming from Alvin. And Alvin is based in Victoria. And Alvin's asking, are there solutions available for the aircraft industry, for example, to vent fuel tank systems, supply a constant airflow in confined spaces? Hiran.
Yeah, sure. So these blowers that we were talking about today are mostly in the wastewater industry. Typically, you'll probably use something like industrial fan or a blower in that type of application, and yeah, you can get that, but it'll be a much lower pressure, and you maybe use it in a more vacuum or pressure type application, depending on if you're sucking the air out or if you're actually blowing the air. But it'll be much lower pressure.
Thank you for that. And over to Ning. Ning's based in Tasmania. Good afternoon. And he's sent a question through to both Jeff and Hiran asking how to design optimized low pressure compressors. How do we design optimized low pressure compressors to address the energy efficiency? Jeff, starting with you.
Yeah, great question. And obviously, it depends very much so on the application. So obviously, the application will determine what technology we use. Also, the control range, how varied is the flow, and what pressure you need. So there's many factors, and that's why engaging with an expert or a manufacturer to seek guidance on that, because there isn't really we can't say that one technology is the best fit for all applications. There's no such thing as that. It's very much a case-by-case basis, and maybe you might need 3 duty blowers and 1 standby, or maybe you need a couple of large base load compressors and some trimming machines of a different technology. There's many ways to skin a cat, for lack of a better term. But yeah, great question, and it very much depends on the very specific application that most plants do have.
Hiran, do you want to comment on that question too?
Yes, please. Yeah, so yes, good question. Power consumption is important, but I think it's also important to look at some of the other criteria when it comes to blower selection, like Jeff was saying. I would say other factors you should look at is noise level, environmental impact, access to service. If you need to get the blower serviced, is that available locally? Even performance characteristics of the application itself. What type of we talked about the water levels varying and, different applications, start-stop applications, things like that. So those things are really important in selecting a blower. When comparing power usage, a wire-to-air approach, I think we mentioned that. I just want to reinforce that. Like the KJI as well as that's ISO standards as well as the ASME PTC 13 are good standards to follow. And it's important to be able to evaluate any kind of blower technology to a standard, because otherwise it's hard to compare technologies, right? So it's important to really apply some kind of a test standard when you're evaluating. Beyond that evaluation, manufacturers should have facilities to perform testing in accordance with these standards. Definitely should consider this type of approach in selecting and specifying blowers.
Thank you, Hiran. And just staying with you for now, and we're zooming around the country, going to Queensland. Good afternoon, Roderick. Was asking Hiran a question. Is there a selection chart showing suitable types of blowers for various volume stroke pressure applications? Thanks, Roderick.
Yeah, I know that's a question I get asked a lot, because everybody wants to, we are used to picking pumps, to tell you the truth. And most of the time, pumping application, you can calculate the flow and pressure and you can pick a pump. Well, when it comes to blowers, there's so many things that can change. You got the environmental conditions that, as we just mentioned, your flow, your water levels can change. So there's a lot more to it than because you're dealing with compressible flow, right? And with compressible flow, the density changes all the time. So you gotta, on a daily basis, the density of the air can change. So inlet conditions for a blower is really crucial, and that's why typically you want to look at kind of a wide range when we're looking at blower selection. So it's hard to just look at just a chart and just pick a blower.
Thanks, Sarah. Jeff, do you want to comment on that?
Oh, no, I think you've covered it quite well, Hiran. But yeah, certainly, as I said before, and as Hiran alluded to, it's very, I guess there's a lot of variables in the blower and low pressure world, from ambient to the demand side and the pressure and all those sorts of things. So yeah, there's no. I wish there was a chart, to be honest, would make both of our lives very easier. But yeah, that's where the low pressure sector is. So no chart.
Thanks, Jeff. And staying in Queensland, good afternoon to Richard, who sent through a question to you both, starting with Jeff, asking, are the energy losses from leaking pipes and joints often greater than the efficiency gained from blower upgrades? Thanks, Richard. Jeff?
Yeah, great question. And again, I would probably say that this actually applies more so to higher pressure ranges, and for sure, air leakage in a traditional higher pressure air compressor station is a thing, and it's not uncommon to see very high percentages of air leaks. And that for sure should be, and can be the easiest way to I guess minimize, energy consumption, as in fixing those leaks. So when we talk about low pressure sector, yes, leaks are a problem, but I guess it's a bit of a less of a problem because we're not so high in pressure. We have more volume and lower pressure, but it still certainly is best practice to certainly minimize leaks, because essentially it's just wasted energy and therefore wasting your money. So yeah, it's important, but not as important as sort of higher pressure systems.
Thanks, Jeff. Hiran, do you want to jump in and comment on that one too?
Yeah, I agree with Jeff that high pressure systems, you will see more air leaks, and you probably hear the air leak. But I can assure you, I have been to wastewater plants where, especially when it's raining, and you'll see the bubbles coming out of the floor of the ground of the soil, the ground, and you realize that you got a leaking air pipe below, and especially because some of these treatment plants are maybe 20, 30 years old, and so you could end up with leaking joint. And so I have seen that a lot. So most of the time when I go to especially old treatment plants, I always look to see. I essentially look from the intake of the discharge to the diffusers, right? I look at all of the things that could be going wrong, and do look for air leakage. And so a lot of the times when we get into these blower upgrade projects, we will look at, because it's not just about replacing the blowers, right? So you got to look at what the piping is like, and if the diffusers need to be upgraded. Electrical is another area. Controls, do you have the proper kind of controls? So all of those things may require upgrade. And so my recommendation is every time a client calls me about replacing blowers or installing new blowers, I always try to understand their system and what they're experiencing there. And actually, a lot of times we will even do a process model to analyze their air demands and understand what their current as well as future air demands are. So that way you're really looking at, even if you wanted to replace blowers, you're still looking at your total system, right? Because to me, that kind of approach is better than just replacing a blower or installing blowers. And just because most of the time you'll find that that's not the only problem that the client has.
Thanks for that, Hiran. Thank you.
Sorry.
Thank you. Thank you. And moving across to WA, we've had a question around legislative requirements from Karthik in WA, asking you, Jeff, how are end users educated about legislative requirements of air compressors? Great question.
It is a good question, and obviously, certainly in Australia, even different states can have different legislations, and different mine sites can even write their own legislation. So it can be a bit of a minefield in Australia, that's for sure. But certainly, when we start talking about higher pressures, there are legislation around design registrations for pressure equipment. For the low pressure sector, often the pressure equipment does fall below the requirement for certain design registration legislation. I'm not saying that's a blanket rule for low pressure, but that's often the case. However, there are standards around for how pipe should be welded and silencers and that sort of thing, and that can be even specific from certain mine sites. But one legislation that we should adhere to is obviously the minimum performance for electric motors, which is our GEM standard. So that's where manufacturers have to log the performance of motors, and that's legislated by the government. There's minimum performance standards for that. So how you can find out about that is obviously having a discussion with the manufacturer, or looking to compressed air bodies like the Compressed Air Association of Australia, for instance, and seeking guidance from experts within the field. So, and I'm sure it's very different in America, but that's sort of how it is in Australia.
Thanks for that, Jeff. Moving over to ACT, we've had a question coming from John to both of you, starting with you, Jeff. And John's asking, what are the impacts of oversizing a compressed air system? Thanks, John.
Yeah, this is a very common thing that we actually see in the industry. So it's a good question that you've asked for, because a lot of the time as engineers, we can get a bit excited with our safety factors, and then all of a sudden things get a size too big, and that actually can be a very big problem. As Hiran alluded to in his presentation, certain technologies do have limitations with control range. So if we were to say we got a flow range and we put one large, turbo blower in there to do the duty, and then all of a sudden the plant fired up and it was only using half its capacity, that would be a very, very problematic situation to be in. So that's where having open discussion with experts and making sure we get the design very, very correct in the first instance to try and avoid that situation, because having blowers oversized is common in the market, and we see that, and it ends up being wasting power and having machines very underutilized, and that affects everything as far as service, maintenance, the whole lot. So it's a situation we don't want to be in.
Hiran, do you want to comment on that?
Yes, I probably, for every right size blower facility I see, I probably see 2 blower facilities that are oversized. Okay, so or too large. A lot of times I see blower facilities that they're wasting air because they can't achieve the turn down they need. And so I always try to advise people, both internally and externally, that one really should look at your aeration requirements, and also, especially when we are working with process engineers, they're very quick to do their calculations and come up with blower sizing. And I always try to question them on what their real air demands are. And so as a process mechanical engineer, it's just a good thing to pay close attention to the blower sizing. And so one is to look at the blower sizing that's there and what their normal operation is. The other is to look at, what your air demands are going to be in the future. Because sometimes, depending on what they're doing in the plant, your air demand may go up or down, population changes, things like that. All of those things impact. So a lot of times you can look at, is it better to, you can certainly maybe look at flexibility in some of the blower selections as well, because you may be able to adjust a few things. You maybe run the blowers at a higher speed or lower speed, or you may be able to adjust the impeller or two, especially if you're talking about multi-stage blowers. So yes, so it's good to look at that kind of flexibility, and also, yes, certainly be very careful about oversizing blowers. It's really good to try to do the right sizing. I know it's not always easy because you're trying to predict, 20 years in the future kind of thing. Yes, definitely.
Thanks, Hiran. And just staying with you now, we've had a great question from Kapila, who's watching from New South Wales, asking you, how does high-speed turbo blower technology compare with the conventional? Thanks, Hiran.
Yes, so I think as I talked about in the presentation, when you say conventional, I assume you mean multi-stage or maybe even positive displacement type blowers. Now, it really depends on the application, right? I think we talked about typical applications and where you would want to use different types of blowers. So a lot of times, I do get the answer to ask this question quite a bit. People are really excited about high-speed turbo blowers. And I do support high-speed turbo, and a lot of the blower systems I design are high-speed turbo blowers. But that's not always the solution, right? On a large plant, if you're going to put in high-speed turbo blowers, you may end up with a whole lot of blower farm, and you don't want to do that. You want to kind of right-size the blower facility and make sure the clients don't end up with these multiples of small blowers, because their size, your size is limited with those blowers. So yes, so it's not the solution for every blower problem, is I guess what I leave you with.
Thanks, Hiran. Question, Jeff, for you coming
One
from Bernard.
If I may add,
oh, yeah.
Sorry, I want to add one other thing. There's also, you can do where you can use the high-speed turbo blowers, but I also mentioned that you can do a base load type situation. So where you can use maybe multi-stage or, especially multi-stage blowers, you can use to base load the blower, the air requirements, and then use the high-speed turbo blowers as a variable flow blower to accomplish the variable flow demand. That may be another option.
Oh, thanks for fleshing that out. Jeff, Bernard sent a question through to you asking, what's the best application between rotary and screw-type blowers? Thanks, Jeff.
Yeah, good question. And again, it gets back to what both of us have been saying all day, is that it really depends on your process. So what you're doing with the air, and certainly the pressure and the flow, and how that would fit within different technologies. So certainly, screw blowers can be a little bit more efficient than we see compared to Lobe blowers, but they do come at a little bit higher purchase price. So there's obviously trade-offs with everything, but yeah, certainly for a little bit higher in pressures, we see that certainly the screws do really come into their own as far as efficiency and that sort of thing. So you can get screw blowers to be over the 1 bar gauge pressure, which you wouldn't really see with a Lobe. So certainly if you need to be in that pressure range, the screw blower would be more advantageous than a Lobe, traditional Lobe.
Thanks, Jeff. We've got a question that's come in about preventative maintenance, Hiran, asking, can you please advise Hiran the frequency required for the preventative maintenance schedule to test and service the blower and the test points to be identified to ensure its operational performance is met? Thanks, Hiran.
All right. So preventive maintenance is kind of like, like even in your car, it's hard to predict when you need, it really depends how you drive the car, where you drive the car, kind of thing. So a lot of times, I find that, maybe when your plant is operating, you can possibly establish based on your, let's say it's a centrifugal, like a single stage machine. You can see how your oil breaks down and stuff like it breaks down, and then kind of decide what's the frequency of servicing. I guess if you're looking for one answer, I would say once every 6 months or so, you probably need to service the blowers. But beyond that, you would probably keep track of how the performance is, because you can monitor things like temperature, oil temperature, bearing temperatures, vibration, things like that. So all of those things, I would say the key to a good blower system is to monitor your gauges, right? Keep track of what they're saying. And certainly walk around, understand your blower, see if it's making any unusual noises, and typically that will help you. As far as testing, I would recommend that you should certainly do factory testing, especially on, maybe not on the real small blowers, but if you're getting into larger blowers, I highly recommend people doing factory testing, and actually doing witness factory testing. So you should have somebody qualified in understanding how the test procedures work and establishing a test plan, and then going and witnessing the factory test. But what's more importantly, you need to establish, and typically when I specify a blower, I establish what the performance requirements are. And I look at the performance range for the blower from a flow and a pressure perspective. I also look at the seasonal variation. So a lot of times you'll get, winter, summer, spring, fall conditions. Because your inlet temperatures and humidity and all that changes, the blower performance changes. So you kind of want to establish that full operational envelope. If you do that, then you pretty much establish that your blower is going to operate under any seasonal or flow variation throughout the year. Now, here's the thing. One thing also to keep in mind is that you cannot truly do a blower test in the field. You can only do what I call a comparative test. You can't do a true wire-to-air test in the field. So the only way to do that is in the factory at a test stand.
Thanks, Hiran. And Jeff, we've had a great question come in asking, based on your presentation, why does the graph for air delivery and specific power consumption have an illogical stroke non-linear curvature? Thanks, Jeff.
It's a good question, and I probably didn't point that out. But like a lot of pumps, and certainly when we talk about air pumps, the I guess you could say efficiency curve of the pump is non-linear, and that's because the pumps do have a I guess, a best efficiency point, and that would be the lowest part of the curve. So certainly when we look at air pumps, really regardless of, well, certainly for displacement, the curves do sort of, I guess, or the pumps, I should say, do get less efficient at low speeds. And also, when we go higher in speed, they can get less efficient. So that's why there's a curve like that. So that's another very, I guess, important factor to look at when we're sort of selecting these blowers, in that we want to make sure that the operation of these units is going to be in their best efficiency point. And that's obviously also very important for turbo compressors, and where they have a very fine control range where they may surge or need to blow off at under 80% utilization or something like that. So there's many factors that come into play when we start talking about running blowers, and certainly we want to make sure that they run at these best efficiency points. So for manufacturers like us, we have software that we can model stations in to be able to really hone in on the combination of compressors and ensuring that they're really running in that best efficiency point at that low point in that graph. So yeah, great question, and that's how, I guess, in tune with design that we're getting with these. It's not just simply saying we want 4 blowers. We're actually looking very purposely at the curve of each blower and making sure that it's going to be running as efficiently as possible.
Thanks. Thank you for Jeff, and thank you to everybody. We've had so many questions come through, and as always, we will run out of time. But I just want to pick out a couple of questions. One has come in through Susantha, for you, Hiran, asking, have you ever installed a blower system for the food manufacturing industry? And is this mainly for blowing away some process materials from the line, or blowing away packing materials from the line? Hiran.
Yeah, I have I don't work too much in the food manufacturing industry, but I have used blowers where we can, you'll have a pressurized line where you're injecting the food, whatever product, and yes, you can essentially use blowers to blow whatever's in the line down. I've used it in not many applications, but you can do that. Yeah, again, you got to look at the application, size the blower properly, and yes, you can certainly do that.
Thanks, thank you for that. And Jeff, just moving on, a question coming in from Ben, and Ben is asking you, is there any difference between the ASME test code and the ISO test document that you referenced in your presentation?
Yeah, good question. And there would obviously be a difference, and I'm not all that schooled on the ASME one because that's actually obviously from, I believe, America. So yeah, obviously it's very country specific, but certainly in Australia we look to a lot of the British standards and what's happening in Europe, because our voltage and measurement system is all similar to Europe, so that's where Australia looks to for those standards. So that's essentially where the ISO standard is born in Europe, and Australia we do try and follow that. So certainly there are some mines that use American standard measurements and that sort of thing. As to the difference between the two, I actually don't know, because I'm not we don't often come up with the American or use the American standards. But I guess it's important that we are all talking, I guess, the same measurement standard, and for sure there's plenty out there, but for CASA and what we use and what I've seen out in the market, the ISO, it's actually the 1217 is what I guess would be the most common in Australia that we use, and so that's from Europe. So yeah, I hope that I know I haven't answered your question, but it's I hope that explains it a bit.
Yeah, thank you for that, Jeff. And as I say, we are about running out of time, and I might sort of close on this question that to you, Hiran. And the question is, at what flow pressure would you consider a blower as opposed to a compressor? Right.
Okay, so I normally consider something over like a pressure ratio of about three times, so if you're increasing, let's say something about, I would say about maybe 2 bar or so above that, I would probably be looking at a compressor. Partly is because you may have interstage cooling and things like that, and your, maybe 1.5 to 2 bar probably is the maximum I would consider a blower. But beyond that, yes, I think you would be probably looking at a compressor. You would call it a compressor. And I know there's a lot of confusion in the industry about what's a compressor and what's a blower. And yeah, there's no real fine, there's no real, broad line there separating the two. So yeah.
Thank you for that, Hiran. And Jeff, I just wondered, do you want to just a couple of wise words to finish with on the topic today?
Yeah, it's obviously been a pleasure to talk about this topic, and it is a extremely meaty subject to talk on, because there's a lot of it's not like just industrial compressors where you can sort of pick off a chart. There is a lot of background design work that needs to be considered, and the process and pressures and flows, and there is actually a lot in it, and obviously more than both Hiran and I can talk about in the space of an hour. But hopefully that's given everyone a bit of a general introduction. And certainly, if there's any more information that you want to ask, Kay's is here to help. And obviously, there's other experts around that are experiencing that field in the low pressure sector. And it really is a fairly unique sector, and it's an exciting sector to be in. So, yeah, thanks for your time and attention.
Thank you, Jeff. And really that is all we have time for today. And please join me once again in thanking Hiran Demel and Jeff Coyle for their time and input. And I would like to stress, thank you, Hiran, because it's now early hours over in Florida. I'd also like to thank Engineers Australia's partner, Kaiser Compressors, for their support. As always, we're looking for your feedback. What can we do better? What can we do more of? So if you could take a couple of minutes and just complete the short feedback form, which is linked in the description box. Thank you again for joining us, and we hope to see you at our next Thought Leaders event. Thank you and good afternoon.